right, welcome back. We talked earlier about Bernoulli's equations and how we derived those. And in this section, we're going to just look at some applications of Bernoulli's equation and some flow measurement devices. So in this course, we're going to focus on four measurement of, or devices that measure flow rate using Bernoulli's equation. The first one, which is incredibly common and very useful, and it's actually very good at measuring flow rates, is a pitot tube or a pitot-static tube. Aircraft use them. They're on high-performance racing vehicles to get good definition or good data on airflow, and they're used to actually measure your airspeed for aircraft. Another one is a Venturi flow meter, which is the device that's used in your lab. Actually looks very similar to this. It is the most accurate method of measuring flow rates, but it can be a bit difficult to set up sometimes. A bell mouth inlet is a flow device. It's kind of interesting. The geometry of a bell mouth inlet allows for no flow to be, I guess, disturbed on the entrance into some sort of tube or tunnel or enclosure. So it's basically just controlling that entry point so that there's no losses and no boundary layer forming in that initial region. And then the fourth kind is called an orifice meter. And if this is introduced into a flow and you know information about the flow behavior through this type of device, you can measure the pressure before and after the orifice meter, and you know what the losses are going to be. You can calculate the fluid flow characteristics that must correspond to those losses. So those are four basic devices. So let's write down the form of Bernoulli's equation again that will be helpful for us as if we write it in terms of our pressures. So we have P plus 1/2 rho V squared plus rho times G times Z is equal to some constant. So we said P is our static pressure. This term, who remembers what this term is called? Our second term, 1/2 rho V squared. Dynamic pressure, good. And P0, yeah, stagnation pressure, and it was equal to P plus 1/2 rho V squared. Good. So the first flow device is a pitot tube, and it makes use of our concept of stagnation pressure. So let's explore this a little bit more. This is a really small diagram, but let's zoom in. So the sum of the static and dynamic pressures is our stagnation pressure. And it represents the pressure at a point where the fluid is brought to a complete stop. So if this is our streamline, right, dead center of this ball that's obstructing some flow, right at this point, we have our stagnation point, which is right here. So that means our velocity at some point 1, v is greater than 0, and at our stagnation point, v is equal to 0. So at point 1, we have velocity just equal to v1, and pressure is equal to p1. And at point 2, let's call this point 2, we have v2 is equal to 0, p2 is equal to p0. So now instead of thinking of this as a ball or some other object, that might not be too useful to us. Let's imagine this is a pitot tube. So what is a pitot tube? A pitot tube is essentially a tube that is open to the facing the incoming flow. So if the flow is in, let's draw it again over here. This is our tube. This is our pitot tube. Let's try and draw this a little better. Let's say we have our velocity fluid flowing in this way. And this streamline is going to hit right in that center of that pitot tube. And if this is water, let's say, then if this is a open to the atmosphere pitot tube, there's going to be some distance h. So a pitot tube, we just define what it is first, is a small right-angled glass tube. Doesn't have to be glass, but some tube with its open end aligned into the flow as to sense the impact or the full impact pressure of the flowing fluid. So a pitot tube is a small right-angled tube with its open end aligned into the flow. And this is to sense the full impact pressure of the flowing fluid. It measures stagnation pressure. And this is because the streamline that is going right to the end of that pitot tube, the fluid inside that pitot tube is not moving. So that streamline is going to come to a zero velocity. It's going to stagnate right at the end of that pitot tube. So the pressure that it'll measure would be the stagnation pressure. And it provides one of the most accurate means of measuring the fluid velocity. So a pitot tube is just a right-angled tube with its open end aligned into the flow. That's the most important thing to remember, and it measures stagnation pressure. So this is a bit different than a pitot-static probe, which I think is what Jason is mentioning. So in a pitot-static probe, it's not just measuring the stagnation pressure, it's also measuring the static pressure. So how it does that is it has a pitot tube system. So we have our, we zoom in on this figure, our inlet for our pitot tube. And then there is a separated region within our pitot tube that has inlets along the side. And they measure the static pressure. So we have a pitot tube and a static tube all as one. So it's called a pitot-static tube or a pitot-static probe. So a pitot-static probe, let's just write this is actually a probe because it's going into the flow on Earth. Pitot-static probe has both stagnation pressure tap and several circumferential static pressure taps. So it measures both stagnation and static pressure. So if we think of the equation that was used for stagnation pressure, we said stagnation pressure was equal to our pressure, our static pressure plus 1/2 rho v squared. So a pedostatic pressure tube can measure stagnation pressure, and it can also get an accurate measurement of the static pressure. So if you have a pedostatic probe, then the difference between these two pressures would equal your 1/2 times your fluid density times the velocity squared. So just one of these devices can actually can be used to calculate the velocity of fluid flow. So let's compare the pedo tube or the pedo probe versus the pedostatic probe. So again, this is just showing on the left-hand side, we just have a pedo tube or pedo probe, and it's just measuring the stagnation pressure. And then we have a 2D cross-section of the pedostatic probe, and it's measuring the stagnation pressure at the end and the static taps on the side. Are measuring the static pressure. And both of these would be connected to whatever device is being used to measure that pressure, some pressure meter. So let's look at actually what's happening in this pedostatic tube. How does this make sense? So in a pedostatic tube, fluid is brought to rest at the mouth of the pedo tube. So right here. Erase. So fluid brought to rest at the mouth. So the velocity at point 2 here would be equal to 0. And then the pedo tube senses the stagnation pressure. So it senses stagnation pressure again. And then the static pressure tap at 1 senses the static pressure. So notice that before we were talking about a pedostatic probe. Pedostatic probe was one device, and it had the static pressure tap attached right to that probe, right to the pedo tube. In a pedostatic tube, we have a slightly different system where we have either of these configurations here is a pedostatic tube where we have a pedo tube that is measuring the stagnation pressure, and then we have a pressure tap along the wall of the fluid flow device. This is typically found in pipe systems, and that's measuring the static pressure at that wall. And if we extend down the pressure to the streamline that is going to that pedo tube, then we can calculate the static pressure along that streamline. So this would be more common for fluid flow, or liquid flow rather. So now we have defined what a pedostatic tube and everything does. Let's apply Bernoulli's equation to this pedostatic tube. This is pedostatic tube system is similar to the system that is in your Venturi lab. So let's apply Bernoulli's equation from 1 to 2. So from point 1 0.2. We have P2 is equal to P0 is equal to P1 plus 1/2 rho V1 squared. So if we know we're measuring P0 from the pitot tube, and we know P1 from the static tube, or the static tap. And if we rearrange this, we can get an equation V1, the velocity at 0.1 is equal to 2 times the pressure difference P2 minus P1 divided by the fluid density rho. So if we measure the stagnation and static pressures, we can calculate the fluid velocity. So let's do an example with a pitot tube or pitot-static probe in an aircraft. So in this question, a pitot-static probe is used to measure the speed of an aircraft flying at 3,000 meters. If the differential pressure reading is 3 kilopascals, estimate the relative airspeed of the aircraft. So first, let's write down our assumptions. So what are some assumptions we need to use in order to use Bernoulli's equation for this flow? What are some things that might pop out at us? Yeah, we're in the atmosphere at 3,000 meters. What is our fluid that we're concerned with here? Is it a liquid or a gas? Yeah, it's air. So what is one assumption that we probably should make if the fluid that we're dealing with is air and we're using Bernoulli's equation? Yeah, we need to assume that it's incompressible. So we can write the airflow over the aircraft. Assume the airflow over the aircraft is incompressible. And so an incompressibility assumption for something flowing through air would be the velocity is less than approximately 0.3 Mach, 0.3 times the speed of sound. Or the Mach number, let's say, is less than 0.3. So beyond incompressibility, what is another assumption we have to consider? And the flow needs to be incompressible, needs to be steady, it needs to have constant temperature. I'll say constant and standard atmospheric conditions. And we'll say the effects of wind are negligible. So that should probably cover most of our assumptions. So in order for this analysis to work, we have to assume all these things. The wind is directly along that vector that's shown V. We have incompressible flow, so we're not flowing through the air too fast. The aircraft isn't moving too quickly. The flow is steady, so there's no wind fluctuations. And yes, good last one, has to be inviscid. Good. So those are our assumptions for this analysis. We can write down some properties. If we look up the properties of air at an altitude of 3,000 meters, we would find that our density of the air would be equal to about 0.909 kilograms per meter cubed. So where should we choose our points? We're going to do our analysis. We're going to have a point 1 and point 2. So point 1 should be at the entrance of the tube whose opening is parallel to the flow. So that could be right here. And point 2 is at the entrance of the tube whose entrance is normal to the flow. Sorry, I'm mixing them up. Point 1 is parallel to the flow. Parallel to the flow is the static port. So point 1 is the entrance of the tube whose opening is parallel to the flow. So that's our static tap port. And point 2 is our stagnation entrance to our pitot tube. And that's where our velocity is 0. And we're going to assume that the Z difference between these 2 points is also negligible. They're so close to the same elevation and relative to the density of the fluid that we're going to say that's we don't need to worry about that. So let's apply Bernoulli's equation. P1 over rho g plus V1 squared 2g plus Z1 is equal to P2 over rho g plus V2 squared over 2g plus Z2. So we end up with V1 squared over 2g is equal to P2 minus P1 over rho g. And just like before, we'd end up with the equation V1 is equal to 2 times P of stagnation pressure minus P1 over rho. And that is because these two terms cancel. And our velocity at point 2 is 0. And so all we're left with is these 3 terms. Yeah, so question in the chat. What we should Google and what we should determine on our own. So far I've noticed that gamma and rho are not always given, but assumed to be known. Are these two the only ones we should Google? Furthermore, is there a more reliable source, such as a textbook table for these? Yes, the properties for fluid densities or specific weights, if I'm not mistaken, let me look, are right inside the front cover of the textbook. So right inside the front cover of the textbooks, you have properties of water at various temperatures. It has density, viscosity, your heat of vaporization, your vapor pressure, surface tension, bulk modulus, and your thermal expansion coefficient. And it has some properties of common liquids. Other than water, it has properties of air, and it has some general properties of some gases. So yeah, all of that is right inside the inside flap of the cover of the textbook. What I might do is I'll find these tables and I'll upload a PDF of these tables to Brightspace so you guys have access to them so you can see them quickly. When I write the problems, I'll try to just give you the value in the question so you don't have to look it up in a table. I trust that you can look up a value in a table. So if we're solving for V1, we have our equation for V1. Let's substitute in some values. Square root of 2 times 3,000 newtons per meter squared. And that is because the differential pressure reading was 3 kPa, so 3,000 pascals. So 3,000 pascals divided by 0.909 kilograms per meter cubed. And let's do a unit check. Do these units work out? Do we have the correct units here? Can we divide pascals by kilograms per meters cubed and get meters per second? What are the units of pascals? Newtons per meter squared. And newtons are kilograms times meters per second squared. And so if we consider this, we have kilograms over kilograms. We'll end up with a meters squared term and a second squared term, and we're taking the square root of that, so we're left with the meters per second. So that all works out. So our final answer would be 81.2 meters per second, or 292 kilometers per hour. So if we look up in our table for air, that has a density similar to this density. We said our density was 0.90. So our speed of sound would be around 370 meters per second. So 80 meters per second is less than 0.3, so we're pretty safe still with that incompressibility assumption. Can we explain why we didn't subtract P1 in the equation? So in the question, it says the differential pressure reading. So the differential pressure reading is the difference P2 minus P1. And then to answer another question from the chat, why does our equation keep changing? Sometimes it's P over rho G, sometimes it's P over gamma, sometimes it's, what is it? What should we choose? Well, all of those equations are the same equation. If we just remember that rho G is equal to gamma, then we can rewrite our equation P over gamma plus V1 squared over 2G plus Z1 is equal to constant rather, not 0. So this was the version of our equation that we wrote when it was in our pressure head form. We had our energy form and we had our pressure form, and they're just whether we multiply these terms by basically rho or G or both. So all of those equations are the same equation. So let's look at a second example. So this question, we have a piezometer and a pitot tube are tapped into a horizontal water pipe as shown to measure the static and stagnation pressures. For the indicated water column heights that are shown in the diagram, determine the velocity at the center of the pipe. So we have our flow. It's going in this direction. And we need to consider the stagnation pressure, which is function of that pressure head. We have the pressure head for the static pressure. We need to find the velocity of that flow at the center line. So if we have to choose the velocity at the center line, that means our streamline point that we need to choose has to be along that center line streamline. So point 1, a common mistake might be to assume that point 1 is over here. Point 1 can't be here because that's not the same streamline as point 2. So we have to choose the same streamline in this flow that is at point 1. So our total pressure head for point 1 is going to be this total water column height, H2 plus H1, which we'll get to in a bit. So before we get too far, let's write down some assumptions. So the obvious ones, we have steady and incompressible flow. And we'll also assume that points 1 and 2 are close enough together that any energy loss between these 2 points is negligible. So we'll assume point 1 and 2 are close enough to neglect losses between them. So we can't use point 1 that's meters and meters away. They have to be fairly close to each other. So we have point 1 is directly underneath the piezometer and it is along that center line, and point 2 is at the tip of the pitot tube. So what is our pressure at point 1? So in the chat, there's a question, can you explain what losses are? So losses would be anything that would significantly affect the flow by, like, basically through friction. If you're disturbing the flow and you're going to measure the pressure at one point and then another point in the flow, and Bernoulli's equation gives you something different than what the flow actually is, it's because of friction typically. So if we have a strong boundary layer or a really long length of pipe, and we're measuring over a huge distance, for example, the pressure loss over that distance, a lot of it would be due to energy loss due to friction from the sidewalls of the pipe, so the viscosity of the pipe. of a very viscous fluid. You can push really hard at one end, and then some distance later, the pressure, static pressure almost goes to zero because there is so much loss in that section of pipe. So we'll get to that a bit later on sort of how do we deal with that, but we don't yet have the tools to handle any sort of losses in our fluid flow using Bernoulli's equation. So let's go back. What is the pressure? How can we calculate the pressure at point 2 if we have these pressure heads that we know? So if we think of the pressure due to a static column of fluid, back to our static fluids, yeah, we have pressure is equal to the height of the fluid column times the specific weight of that fluid, which is rho times g. So we have rho times g, and for point 1, we have to consider the total height of that water fluid column from the center line. So that would be h1 plus h2. For pressure 2, we get the same thing, rho g, except now we have to add up h1 plus h2 plus h3. And we know also that z1 is going to be equal to z2 because they're at the same point. And we have v1 is unknown, asking to find the velocity. And we know v2 at the stagnation point is going to be 0. So let's write down Bernoulli's equation again. Which form do we want to write it this time? We could just leave it at the same time, but we've already solved that equation for v1. So let's just go straight to that equation that we derived already. v1 is equal to the square root of 2 times P2 minus P1 divided by rho. So that's equal to 2. P2 was equal to rho g times h1 plus h2 plus h3. Minus rho g times h1 plus h2, all divided by rho. So in this, we're going to have some terms cancel out. We have rho g times h1 plus h2 minus rho g times h1 plus h2. So the only term left over is rho times g times h3. And we have rho divided by rho, so we're only left with the square root of 2 times g times h3. So that's equal to 2 times 9.81 times h3 is 0.12 meters. So our final answer, 1.53 meters per second. So that's pretty much pitot tubes and pitot-static tubes. We start with our equation right here, which will help us find the unknown velocity. Typically, these devices are just being used to determine the velocity of a fluid flow. All right, let's look at the next device. The next device that we can consider is something called a bell mouth inlet, and it itself is a flow measurement device. So what it looks like is if we imagine like a trumpet horn and flow is going into the bell end of that trumpet horn, we can consider fluid at point A and fluid at point B. Fluid at point B will have some velocity VB, and at point A will have some velocity VA. But that distance that's far away at VA, we now consider VA is equal to 0, and the pressure at point A is equal to the atmospheric pressure. And then some short distance inside our bell end, we have a static tap. And that static tap is measuring the pressure PB. So that's the static pressure at point B. So at this point, our flow is essentially one-dimensional since it has not been affected by boundary layer, and there's no slip at the wall for that very, very short length. So flow is essentially one-dimensional since it has not been affected by boundary layer. So the flow is one-dimensional, it's not affected by the boundary layer, and there is no slip at the wall for a short length. So we're kind of breaking that no slip condition as long as that static tap is located very close to the entrance of that bell mouth. So here's another diagram. So some assumptions with a bell mouth inlet. We have to assume that we have frictionless flow along streamline from 1 to 2. So if we have point 1 to point 2, and this is along a streamline. Which is a reasonable assumption for a smooth pipe and a bell mouth inlet. So this is reasonable. So if that's the case, we can write Bernoulli's equation again. So let's write it in this form: P2 plus 1/2 rho V2 squared plus rho G Z2 is equal to P1 plus 1/2 rho V1 squared plus rho G Z1. So we said that point 2, or if we wanted to separate this between point A and point B, let's just double check. Point A was our point far away and point B was our point close away, or close to. So we can rewrite this as PA plus 1/2 rho VA squared plus rho G ZA is equal to PB plus 1/2 rho VB squared plus rho GZB. So we said our pressure at A was our atmospheric pressure. Our velocity at point A was 0, and we're assuming that our elevation is negligible, or ZA minus ZB. So we only have P atmosphere on the left-hand side, and on the right-hand side, we have the pressure tap PB plus 1/2 times density times VB squared. So just like with our pitot system, we have VB is equal to the square root of 2 times now P atmosphere minus PB over the density of the fluid. So the difference between the velocity calculation for a bell mouth and the velocity calculation for a pitot-static tube is we're using our atmospheric pressure instead of that stagnation pressure. So remember over here we had P2 was our stagnation pressure. If you ever forget these equations, just remember one form of Bernoulli's equation and you can always find these equations. So our next flow device is a Venturi meter. So this is going to be exactly what you're going to be looking at in your first lab. So a Venturi meter is a smooth, convergent, and divergent section of pipe. So it's really important that it's smooth and gradual. So we're not having very, very sharp changes in geometry. They are gradual changes. And that is to reduce the effects of any losses or friction. So we have a smooth, convergent, and then divergent section of pipe. And it's the most efficient flow rate measurement device. I guess flow rate measurement device we should write. And the only issue with it is it's a bit expensive to build and implement. So why wouldn't we always just use a pitot tube? A pitot-static tubes are quite useful, and they have their specific applications. Venturi meters are quite useful when we have a contained flow within a tube. Pitot-static tubes tend to be used much more often when we have an open system. So we have a body that's flowing through an open fluid, and that's where it has its advantages over something like a Venturi meter. So how does it work? So what we do is we measure the pressure P1 and P2 at 2 points, some point in the inlet or some distance away from what we call the throat. The throat is the narrowest section. And we use Bernoulli's equation along the streamline between these 2 points. And we treat it as a 1D, one-dimensional frictionless flow. So 1D so we can write P1 plus 1/2 rho V1 squared. And if there's no change in our elevation Z, we can leave out those Z terms. And that's equal to P2 plus 1/2 rho V2 squared. So now we don't have a point in our flow where the velocity is 0. So we have all of these terms remaining. So let's just separate our pressures and our velocities to either side. So we get P1 minus P2 on the left-hand side. And on the right-hand side, we have 1/2 times rho factored out V2 squared minus V1 squared. So let's write this as our first equation. So just by measuring this pressure difference, we can figure out a velocity difference, but we can't figure out what the absolute velocity is. So we need another relationship that will help us determine these velocities. So if we look at our Venturi meter, we know some information about the areas. We know the area at the inlet or at some point, and we know the area at the throat. So if we know the areas, and if we have a steady incompressible flow, that means that our flow rates through these two cross sections is the same amount of fluids going through. If we had more flow entering at point 1 than there was flow leaving at point 2, then that section of the Venturi meter would be accumulating mass. It would just be getting denser and denser as we packed more fluid into it. So that wouldn't be steady continuous flow, that would be a transient flow. So this only works for a continuous flow, which means that the flow rates of these two sections, our Q values, have to be the same. So because our flow is steady, Q1 must equal Q2, which is just equal to, we'll call it our flow rate. So if that's the case, our flow rate we defined before as our area times our average velocity. So our area at point 1 times the velocity at point 1 must be equal to the area at point 2 times the velocity at point 2. So this would be our second equation. So if we put those two equations together, we get Q is equal to V2 times A2, which is equal to A2 times the square root 2 times P1 minus P2 divided by rho times 1 minus A2 minus A1 squared. And this is what we called, or what we would call, our ideal flow rate. And this is based on measuring P1 and P2. So this is only accurate if we have one-dimensional and frictionless flow. And remember when we talked about one-dimensional flow? One-dimensional flow was what we called our fully developed flow. So that means our boundary layer has found an equilibrium. It's not still developing, so our flow is not changing along the length of our Venturi meter. Is it 1 minus, oh yes, I forgot some brackets. So yeah, it's rho times that entire denominator, which is 1 minus the fraction a2 over a1 squared. So if this is our ideal flow rate, and we have a real system that is not perfectly frictionless and maybe not perfectly one-dimensional because it is a flow developing as we move through the Venturi meter, we need to introduce some sort of correction. So how do we compare our actual flow versus our ideal flow? So for the same pressure difference, we have an actual flow rate which we'll call Q actual. And it'll be a bit different. Slightly different. And we can introduce a coefficient called the Venturi or discharge coefficient that relates the actual flow rate and the ideal flow rate. So let's define a Venturi, or what they call in your textbook, a discharge coefficient. And that discharge coefficient is CD is equal to our actual flow rate divided by our ideal flow rate. So if we do this, then we can rewrite the actual flow rate equation as Q actual is equal to our discharge coefficient times the area of section 2. In the diagram above, section 2 was at the throat, times the square root of 2 times P1 minus P2 divided by rho times 1 minus A2 squared over A1 squared. So it's the same equation, I just wrote it slightly differently in the denominator. Maybe it's a little more clear. So this equation is our actual flow rate. So in your lab, you are essentially going to be measuring the pressure difference between the throat and many points along your Venturi meter. And that'll be measuring your actual flow rate. And you're going to compare this, you're going to know your actual flow rate, and you're going to compare this with the ideal flow rate. and you're going to try to calculate what the discharge coefficient of your Venturi meter is. So for many flow devices, there are several flow coefficients that define the difference in the flow from an ideal flow to the actual flow. So we just talked about the discharge coefficient, and the discharge coefficient is actually a combination of two other coefficients, the contraction coefficient and the velocity coefficient. The velocity coefficient is just the ratio of the actual velocity divided by the ideal velocity going through a flow device, and the contraction coefficient is the ratio of the area of the flow stream after the flow device divided by the nominal area, so the area of an ideal flow device, the geometry of that flow device. So for a Venturi meter and a bell mouth, we tend to have values around here. So this would be a bell mouth and Venturi meter. We tend to have values around here. So we don't need to worry too much about what these values mean and how we calculate them, but I just want you to know that they exist. And it's oftentimes that we will find the discharge coefficient will be a function of the actual flow rate. So depending on how fast your fluid is flowing through the device, it will change. And so we can plot our discharge coefficient versus our Reynolds number, which is a dimensionless parameter that has to do with the geometry of the flow device, as well as the velocity and density and viscosity of the fluid itself. So we have usually pretty high discharge coefficients for Venturi meters. So the actual flow is pretty close, 98 or 99% of the ideal flow. And this is why it's considered the most efficient way of measuring flow rate, because it involves very little energy loss. That discharge coefficient is almost 100%. So let's do an example with the Venturi meter. So in this question, we have air flowing through a Venturi meter whose diameter is 2.6 inches at the entrance. So that we'll call location 1, and 1.8 inches at the throat, location 2. The gauge pressure is measured to be 12.2 psi at the entrance and 11.8 psi at the throat. Determine the flow rate of air and take the density of air to be 0.075 pounds mass per foot cubed. So we have our diagram. Let's assume we have our assumptions so that we can write Bernoulli's equation. We have steady incompressible flow, and we want to find now the flow rate. So determine the flow rate of air. It doesn't give us any information about the discharge coefficient, so we're going to assume that we're looking for the ideal flow rate of the air. So we can write down our equation for flow rate. So from Bernoulli and continuity, we have Q is equal to V2 A2, which is equal to A2 times 2 P1 minus P2 over rho times 1 minus A2 over A1 squared. So we have the flow rate, or we can determine the flow rate if we just substitute in the values that we know. We can change the areas. We know the ratio of the areas is going to be equal to the ratio of the diameters squared. So we can simplify that. We think of A2 over A1 is equal to pi d2 squared over 4 divided by pi d1 squared over 4. The pi over 4 terms divide to 1, and we're left with d2 squared over d1 squared. So if we know the diameter of those sections of our manometer, or not our manometer, our Venturi meter, then we can rewrite our equation as Q is equal to A2, so that's pi times diameter 2 squared over 4 times the square root of 2 P1 minus P2 divided by rho 1 minus D2 over D1 now to the power of 4. So let's substitute those values in. Pi, the diameter of section 2. So section 2 we said is located at the throat. So this is 2, this is 1. So our diameter is 1.8 inches. So 1.8 over 4. Pressure at 1 is 12.2 minus 11.8 times rho, which is given as 0.075 pound mass per foot cubed. So 0.075 times 1 minus, we have 1.8 to the power 4 divided by 2.6 to the power 4. So we need to do some conversions here. We have units of PSI at the top, and we have pound mass per foot cubed at the bottom, and we have an area in inches. So our units at the top are PSI, and our units at the bottom are pound mass per foot cubed. And over here we have unitless. We have area divided by area. So if we have pounds per square inch, we have pound force and pound mass, and we have inches and we have feet. So we have to do 2 conversions. And this is all going to be inside the square root. So our first conversion will be 144 pound foot per foot squared per 1 PSI. So when we have our pressure in terms of pound force per foot squared, and now we need to go from pound mass to pound force for the denominator. So that's 32.2 pound mass times feet per second squared per 1 pound force. So whether you decide to do it this way, or if you change all units before so they're equivalent units, either method is fine. And our final answer we would get would be 4.48 feet cubed per second. Or cubic feet per second. So the flow rate through this Venturi meter would be 4.48 cubic feet per second. So we have a little bit of time. Let's start one more example. So a construction in a pipe will cause the velocity to rise and the pressure to fall at section 2 in the throat of a Venturi. The pressure difference is a measure of the flow rate through the pipe, and the smoothly neck down system is called a Venturi tube. Find the expression for the mass flux in the tube as a function of the pressure change. So let's first, we assume that the tube is horizontal. So we have point 1 and point 2. Let's just start by writing Bernoulli's equation. It's asking us to find an expression for the mass flux. So the mass flux is basically the mass flow rate. So Bernoulli's equation, we'll write Bernoulli, P1 divided by rho plus 1/2 V1 squared plus G times Z1 is equal to P2 over rho plus 1/2 V2 squared plus G Z2. So if Z1 is equal to Z2, so we assume it's horizontal, and we can solve for V2. And we get V2 squared minus V1 squared. So the difference of our velocities squared is equal to 2 times delta P, or P1 minus P2, our difference in pressure, divided by rho. So we have one equation. Our next equation that we can use for incompressible steady flow is our continuity equation. So our continuity equation, Q1 is equal to Q2, so we have A1 V1 is equal to A2 V2. And so we can write the ratio of our areas would be equal to the ratio of our velocities. So V1 over V2 would be equal to A2 over A1. And like we just said before, this is equal to the ratio of our diameters squared. So D2 squared over D1 squared. This is our second equation. So let's substitute our equation 1 and 2. So 2 and 1. And let's simplify. Let's just use a factor beta, and we'll say this is D squared, D2 squared over D1 squared, just so we don't have to write so much. So we substitute this into our equation 1. We get an equation V2 is equal to the square root of 2 times P1 minus P2 divided by rho times 1 minus b to the power of 4. So this is the equation for our ideal velocity. If we had multiplied this by A2, we would have our flux. So this is a velocity at point 2. And then the mass flux is m dot. And m dot, our mass flow rate, is equal to the density times the area cross section times the velocity at that cross section. So we think back to our definition of our mass flow rate, our mass flux, be rho A2 V2, which is equal to A2 times the square root of 2 rho P1 minus P2 over 1 minus beta to the 4. So this rho over here, we brought it inside the square root sign, so we had a rho squared on top and a rho in the denominator, so we just have a rho left over in the numerator. So this is our definition of our mass flux. At the throat of a venturi, if 0.2 is the throat. And remember, because we didn't use the discharge coefficient, this is the ideal. So let me just look at the chat quickly. So why would that answer be squared and not to the power of 4? Well, our ratio in the equation is a2 over a1 squared. And if a2 over a1 is equal to d2 over d1 squared, then we just square it again. So it's to the power of 4. So our beta is to the power of 4. So that's it for today. I'll send out an email probably tomorrow morning with information about the midterm. Let everybody know that it's not going to be on Tuesday. It'll be next Thursday, and we will also all have a office hours on Monday for an hour, so that you can ask questions about the midterm or just general questions about course content so far. Since you only finished half the lecture, is the mini quiz still due tomorrow? Yes, the mini quiz is still due because the mini quiz only covered up until this point. Beta would be the power of 4. Yes, if beta, sorry, yes, beta is our definition. Let me correct that. It is not squared here. Thank you for that. It's just d2 over d1. Yes, sorry, that's my mistake. Beta is just, we're going to call that d2 over d1, the ratio of our diameters. So yeah, that's that. Let's scroll down for what we missed, and we'll just get to that quote, and I'll have to come up with a new quote for next week. The quote for this week, there is virtue in work and there is virtue in rest. Use both and overlook neither. And this is written by an American author, Alan Cohen.